electrical potential difference, also known as electromotive force or simply cell voltage, is the difference in voltage between the anode and the cathode of an electrochemical cell or a voltaic cell. Now this difference in voltage between the anode and the cathode allows these electrons to flow from the anode to the cathode. A positive cell voltage indicates that our reaction within our electrochemical cell is product favored, so is spontaneous. Likewise, a negative cell voltage indicates a reactant favored reaction. Recall that Gibbs free energy builds a relationship between enthalpy and entropy, and it also dictates whether a reaction is product favored or reactant favored. So notice that both cell voltage of an electrochemical cell and Gibbs free energy dictate whether or not a reaction is product favored. So therefore we can imagine that there is some type of relationship between cell voltage and Gibbs free energy. Now when Gibbs free energy is positive, that means our reaction is reactant favored. It's not spontaneous. But when it's negative, the reaction is product favored. It is spontaneous. Now before we actually build a relationship and show how the cell voltage relates to Gibbs free energy, let's examine something called electrical work. Now we already spoke about electrical work when we spoke about electromotive force, but let's revisit this topic because it becomes important. So voltaic cells or electrochemical cells convert chemical energy into electrical potential energy that can be used to do work. For example, power a light bulb or power a motor. Now this electrical potential energy is also known as electrical work. And we can express electrical work mathematically by equaling this guy to charge of an object or a system times our cell voltage. So if we're talking about cells and electrochemical cells, our charge refers to all the possible charge in our battery, in our chemical cell or electrochemical cell. Now recall that a single electron has a charge of 1.6022 times 10 to the negative 19 coulombs. This is per electron, per one electron. But obviously a single battery, a single electrochemical cell has many electrons within itself. That means we're dealing with a lot of these guys. Now let's find how much charge is in 1 mole of electrons, right? The way we do it is we use Avogadro's number. Remember, Avogadro's number refers to the number of atoms or electrons found in 1 mole of anything. Now if we're talking about 1 mole of electrons, that means we take this number of electrons and we multiply it by our charge per electron. We see that Avogadro's number of electrons per mole times 1.6022 times 10 to the negative 19 coulombs per electron, which we got from here. The electrons cancel and we get our units to be coulomb per mole. So the charge of a single mole of electrons is 96,484 coulombs per mole of electron. So when we have 6.022 times 10 to the 23 electrons in our cell, that means our cell has a charge of 96,484 coulombs. So we can represent this equation in another way. So this equation, electrical work, is equal to N, the number of moles, times F. Now F is Faraday's constant. This number is known as Faraday's constant. And it talks about a charge of 1 coulomb per mole of electrons. So once again, F is Faraday's constant times our cell voltage. So this N times F is simply charge. It's the same thing. Now for example, if we have 1 mole in our cell, that means we multiply 1 mole times F. So 1 mole times this guy gives us the moles cancel and we simply get our charge. So N times F is our charge. Now this equation becomes important when we build a relationship between our cell voltage and Gibbs free energy. So let's see what the relationship is. So let's finally examine and see what the relationship is between cell voltage and changing Gibbs free energy. Well, we see that changing Gibbs free energy is equal to a negative of electrical work done. Well, why is that? Well, this guy is simply the amount of free energy available to do useful work. While this guy, the electrical work, is the amount of energy transformed from chemical energy to electrical energy in the form of moving electrons. And this is also energy used to do useful work. So that's why the magnitude of these guys is the same, but the sign is different. So why is it that we have a negative sign in front of the electrical work? Well, let's see why. The negative sign accounts for the fact that for a product favored reaction, changing Gibbs free energy is negative, while cell voltage is positive. So that's why we need to add that negative sign in. So from before, we saw that electrical work is equal to number of moles times Faraday's constant times our cell voltage. So changing Gibbs free energy is equal to negative N times F times cell voltage. So that's our reaction. That's our equation. Now suppose we have an electrochemical cell, a voltaic cell, that's composed of the following redox reactions. So it has an oxidation reaction and a reduction reaction. Our zinc solid is oxidized into zinc ion, while our copper ion is reduced to copper solid. So this guy releases 2 electrons, while this guy takes those 2 electrons, gains 2 electrons, forming our copper solid. Now these electrons in the end up crossing out. Now our cell voltage is 1.1 volts. So let's use this formula to approximate how much energy this battery or this electrochemical cell can produce with the charge that it has. So the change in Gibbs free energy is equal to negative of the number of moles of electrons. Well, in this case, I specifically left these guys in to show you how many moles of electrons we have. Well, zinc loses 2 moles of electrons, and this guy gains 2 moles of electrons. That means we're dealing with 2 moles of electrons. Times our Faraday's constant, 96,500 approximately, coulombs per mole of electron, times our cell voltage or electromotive force, 1.1 volts. We see that these guys cancel out, and our units are left coulombs times voltage, which is simply joules. So in the end, we get 212,300 joules of work is produced, is released in the form of moving electrons or moving charge from the anode to the cathode from this battery. And this amount of energy can be used to do useful work. For example, run a motor or power a light bulb, for example. So this becomes very useful, and we'll do many more examples using this in the future. So I already spoke about this briefly in another lecture, but I want to talk about it once more. Now the reason that a D battery has more energy than a AAA battery is not because a difference of cell voltage. In fact, the cell voltage for this guy and this guy are the same. It's 1.5 volts. You could check the label of the batteries. The reason this is more expensive is because it can do more work. But how can it do more work? Well, because this guy has a larger N. It has more electrons than this guy. It has a larger charge. So this guy, for example, can run a light bulb or power a light bulb for 15 minutes, while this guy can power a light bulb for much longer because it has more charge, a larger N value than this guy.